You started the lecture by giving numbers for the weak charge of the proton and neutron. Can you say a few words about what weak charge is and why it's so different from the neutron?
Weak charge is actually a reflection for the part content of this nucleus. And this is in principle like you can write down the nuclear current, and you have this is a 4-vector current, and you have the 0 component, which is the density, and the vector part of the current. So you can do it for the electric current. You can do it the same way also for the weak interaction. And then you will have vector weak current and axial vector weak current. And with that, you can couple again to this Z-naught exchange the electron to the system. But because this is parity violating reaction, the way, the difference, you are not sensitive to the gamma, but only to the exchange of zero. If you want what is being done, well, I have to go all the way back. This process of electron scattering on any nucleon is the sum of these two directions, okay? If you have no charge exchange. So it's either you exchange a photon or you exchange a xenon. Now, the gamma photon couples the charge, the normal electric charge. And the same way you may regard the Z-naught as being coupled to some different charge, which we call fluid charge.
Sorry,
when you have two nuclei,
You have one.
maybe you can rephrase of the same question. What would be the weak charge of the up and down force? I mean, that's it.
And I don't know that by heart, I'm sorry.
Isn't it like one size?
Of course. But it is reflected in the weak charge of the electron proton.
so if you have two nuclei and you get you solve two different nuclei, do the parameters of the two body force in the two nuclei, are they the same or different? Or do the parameters of the two body force in one nucleus depend on the parameters of the 3 and 4 and 5 particle force?
No.
No means what?
No means that interaction is independent of the system. It's like don't expect the Coulomb force
So the
to be
two
different.
body force is the same for all nuclei.
Yeah.
Then why is there a problem with 52 nucleons? Because you should have solved all the steps up to that. Okay, you don't have to correct what you have already solved.
You are right, but for two problems. First problem is that to solve for 52 nucleons is difficult.
That's the reason you do it.
Yes, of course. Therefore, some approximations need to be done. It's not that you solve the three-body problem that you know that you can get arbitrary accuracy. So this is one thing.
You mean
Second
if you solve three-body problem and you go to the fourth, you have to resolve the first?
No.
You don't have to.
For the four-body, I have to solve the four-body from scratch. Nothing that I've done before is used in this sense.
So you may get that the two-body force with the 4 particle is different from the two-body force with 2 particles.
No, I will look at it differently. I have the Miami Hamiltonian, okay, with all these fancy diagrams, okay, what is that? I have my potential. Okay. Now I fitted the parameters. Okay. This
So you fitted the
20
parameters
parameters to the 2-body and 3-body systems.
now you go to the higher nucleus.
Now I go to higher, larger system and make predictions. And I see whether I manage to reproduce the experimental data or not. If I manage, then the theory is successful. If it is not, there is a problem with the theory. Now there are two possibilities. One is that the theory is not complete, and I have to take into account more diagrams, calculate them, and see if I manage to reproduce the experimental observation. This is one possibility. This is a positive thinking possibility, if you like. Then there is another possibility. Another possibility is that these larger systems are actually, to a large extent, need a very fine-tuned set of parameters. That is, that if I try to fit my parameters in a 2- and 3-body system and make predictions, I am not sensitive enough. And I might fail because I really need some kind of fine-tuning of these parameters in order to really reproduce all the wealth of data that is available. In that case, then I will have to make some compromise and maybe pick some larger systems, use them to fit these parameters, and predict all the rest. At this point, it is not clear what is the situation, whether we have a predictive power or not, whether we just need some diagram or we need to do the fine-tuning. My personal belief is that eventually some fine-tuning will be needed, because starting from 2 and 3 particles and predicting all the rest
So there is
seems to be very difficult.
So there is definitely possibility that with 4 particles, the 3-body force changes at least a little bit.
No, I don't. This is not the way I would do it. It's not the force that is being changed. The force is always the same 3-body force. Because in principle, in this EFT, you took into account all possible interactions. Okay? And you systematically sort them order by order. If you want to see what happens, especially in the 4-body system, it is the appearance of this 4-body force. But we know what to expect. We know to estimate, based on this power counting, what should be the size of this force. And it is expected to be at the level of sub%. So this is not a big effect.
I will let you converge later.
Something different as an experiment, expert on nuclear physics. Anything new about the island of stability?
It's not that part of the. There was a recent measurement in Japan of some very heavy nucleus. But you mean this part of the world?
Which was predicted there may be some stable
real evidence for stable nuclei there. This is invisible.
And from what you said from theory,
well, at the theory we are not yet at the level, okay, at least I believe the theory, we are not yet at the level to make any predictions. This will take at least a bit.
More questions? If not, let's thank Nir.